So welcome everybody. So now we'll have Henry Yuen, who will be telling us about complexity theory for fully quantum problems.
Can everyone hear me? Yeah. All right. Hi, everyone. Thanks so much for giving me the opportunity to speak here. This talk is going to be about attempts at trying to understand the complexity of what I call fully quantum problems. And these are computational tasks that have quantum states as inputs as well as outputs. And these types of fully quantum problems appear to be quite different in nature than the types of computational tasks that are typically considered in complexity theory and computer science, those with classical inputs and classical outputs. And these fully quantum tasks naturally arise often when you're thinking about quantum information theory, quantum cryptography. And as we're starting to see, they're also starting to come up very naturally in considerations in high energy physics. And in this talk, first, I'm going to try to motivate why I think we need a complexity theory for these types of problems. And then I'll try to present pieces of what I think this theory could look like. All right, so I'm going to start off with a scenario that should be quite familiar to many of you in this audience. And suppose you take a qubit, an entangled qubit, so it's entangled with something far away, and you throw it into a black hole. Right? And you wait some time, the black hole radiates, the black hole shrinks. And the question that you're interested in is, where can I find this qubit? Is it possible to retrieve the state of this qubit that you threw in? And one of the things that we know is an argument that Hayden and Preskel and probably others have observed is that if you think that the evolution of the black hole and the radiation is described by a unitary process, then after some time, the page time, the qubit should be recoverable only from the state of the radiation. Right? So now this external qubit should be fully entangled with the radiation. And this is quite interesting. And I guess after some years, people realized that this observation led to some apparent paradoxes. So for example, this amps paradox. Then further, this led to some attempts at a resolution. How do you get around this paradox? And one possible resolution is the consideration of complexity. So in a paper by Harlow and Hayden, they said that, well, in principle, you can recover the state of the qubit just by acting only on the state of this radiation. But from computational complexity considerations, it should be intractable to actually do this decoding. And their argument combined with the strengthening provided by Scott Aronson can be phrased a little more precisely as the following statement. So if you assume that something called a cryptographic one-way function exists, so this is a function that can be efficiently computed in the forward direction, but difficult to invert in the, difficult to invert. Such an assumption is essential and crucial to essentially any form of cryptography that we have today. So if you make such an assumption, then in principle, there exists a state of the black hole and radiation from which you can prove that the qubit cannot be recovered in polynomial time. This is the conclusion of the Harlow, Hayden, and Aronson argument. So that's quite interesting. So after this, some natural questions arise. So first question is, well, if this really is a resolution of some of these important paradoxes in quantum gravity, can you derive the conclusion from, say, a weaker assumption, or perhaps no assumption at all, right? I mean, we, in the computer science world, we all believe that one-way functions exist, or we hope that they do. I mean, it's essential for cryptography, but this is not yet a proven thing. I mean, proving this is essentially as hard as proving the P versus NP question, right? So ideally, you'd like to have a resolution that doesn't depend on such an assumption. So that's one question. Another question could be, does this hardness of decoding this qubit, does this hold for generic black holes? right? This argument that they provided, they construct a seemingly artificial state of a black hole and radiation that intrinsically embeds a one-way function inside. And you can ask, well, is that something that you are likely to encounter in nature, right? So that's a reasonable question to ask. And this argument says that even if you believe you can extend this hardness for generic black holes, okay, so it says, all right, this task of given the state of the radiation, distill out this qubit that you threw in long ago should be difficult. Even if you believe this, you can ask, well, just how hard is it? I mean, it should be hard, but not all hard problems are created equal, right? So you can thinking, from the point of view of computer scientists, you can ask, if I have limited resources like limited space, limited memory, or if I allow myself non-determinism or post-selection or computational resources such as these, can I use them to efficiently decode Hawking radiation? So these types of questions, you look at them and you see that they're really firmly ensconced in, you're really asking about the computational complexity of a certain task, and you'd like to answer them somehow. So you look around and you say, well, maybe this is, we already have a theory to answer these types of questions. And in fact, there's a paper written over 30 years ago by some of the organizers of this workshop titled Quantum Complexity Theory. And it seems like a promising title to a theory that could answer some of these questions, right? And in this paper, this is absolutely foundational to quantum computer science. In this paper, it codified this notion of quantum polynomial time, represented by the acronym BQP, represents the set of problems that you can solve efficiently on a quantum computer. And of course, the biggest question in the area of quantum computer science is to really tell whether BQP contains problems beyond P, the set of problems that you can solve efficiently on a classical computer. This quantum complexity theory has developed over the last 30 years, and it's been absolutely given us wonderful things. We have a rich zoo of complexity classes, starting with BQP, quantum polynomial time, but we also have complexity classes that capture the notion of post-selected quantum computation. We have this class QMA, which is the quantum version of NP, right? It captures the difficulty of estimating ground energies of local Hamiltonians. MIP star, which captures an esoteric model of interactive proofs with entangled provers. There are interesting computational problems that have arisen by thinking about quantum complexity theory. The problem of simulating a Hamiltonian on a quantum computer, approximating the Jones polynomial, or estimating the ground energy. It's also given insights into many fields like Hamiltonian complexity, operator algebras, and more recently, this quantum complexity theory has given us a rigorous theoretical foundation to really understand when do we get advantage with quantum computers. So it's been a very successful theory with lots of wonderful insights. But you step back and you look at this theory and you realize that so far, for the most part, it's really been a theory of computational problems that are classical input, classical output, right? We're really thinking about problems where, the thing you're trying to solve is really there's some question or some instance that's specified by some classical string. And at the end, you want some classical string as output, maybe a number, maybe a yes/no value. And the only thing quantum about this is the model of computation that you're considering. So, simple examples, the factoring problem. We all know that quantum computers are very good at factoring, but it's a classical input, classical output problem. You give in as input an integer n, and the outputs are the factors of the integer. Here's another problem, the local Hamiltonians problem. You give in as input to this problem a description of a local Hamiltonian. You write down on a piece of paper. And you hope that the output, the thing you want to obtain is a number, right? An estimate of the ground energy. And in quantum complexity theory, the model of computation that we're considering is often in this case is this QMA verifier prover protocol. right? Never mind what that is at the moment, but it's some quantum model of computation. Okay, so that's formulating things in this way makes a lot of sense because with these classical input and classical output problems, we can meaningfully compare the power of classical computers versus quantum computers, right? Because after all, classical computers can only deal with problems that have classical input, classical output. And it also allows us to connect quantum complexity theory with the vast body of knowledge that we've gained in classical complexity theory. So an interesting statement that you can make is the task of boson sampling is hard for classical computers unless the polynomial hierarchy collapses. This gives very interesting and good evidence that the task of boson sampling is computationally intractable. Okay, so but let's think more broadly, and we do live in a quantum universe, and we oftentimes come across quantum computations that don't make sense on classical computers, right? And these are quantum in, quantum out problems. So here's an example. So let's take the task of preparing some complicated quantum state, right? So let's imagine that the input to this problem, it's still classical. It's a description of a local Hamiltonian that you've written down on a piece of paper. But now, as output, you don't want just a number. You actually want a collection of particles whose quantum state is the ground state or a ground state of this local Hamiltonian, right? Obviously, only a quantum computer can perform this task, but it's a very interesting one, an important one, and you might ask, how hard is it to perform such a task? Here's another example, classifying quantum phases of matter. So here, the input to the task, to the problem is a quantum state. So maybe it's some quantum state in an unknown phase. And the output of the quantum computer should be some phase label. Okay. And here's something that's a fully quantum problem. Again, let's take the radiation decoding problem. The input is the state of the black hole radiation, and the output should be the qubit that you tossed into the black hole long ago. All right, so these are very natural, quantum tasks that we think about a lot in our field, and one wonders, can quantum complexity theory explain when these tasks are easy to perform or when they're hard? And what's really interesting is that recently we're starting to get some evidence and some insight that quantum complexity theory, this rich theory that we've built over 3 decades, has started looking incomplete for the purposes of answering these questions. So let me go a little more into that, and that's going to take us through a detour through quantum cryptography. And so I'm going to tell the story of quantum bit commitments, which is a concept from cryptography. And first I have to explain what a bit commitment is. It's a cryptographic analog of putting a message in a sealed envelope that is opened later. Okay? Formally speaking, a commitment protocol involves 2 phases. There's a commit phase and a reveal phase. So let's see, is this the laser? So in the first phase, this commit phase, there's so there's 2 parties here. There's a committer who is thinking of a bit B. And so you can think of this bit as maybe a vote that they're trying to commit to, or maybe a bid or something like that. And they're going to send a commitment to this bit to someone called the receiver. And in this commit phase, they're going to talk back and forth in some way. And at the end of this phase, the receiver should have some piece of information, this the analog of the sealed envelope that has the commitment C. And what's important is that this receiver should not be able to tell what is this bit B just by looking at this sealed envelope, right? We can just think for now that the envelope is kind of hard to open. All right. And we say that this protocol, or this commitment scheme, satisfies what's called hiding security. So this commitment does not reveal the bit B to the receiver. In the second phase, after some time passes, at some point the committer will decide to reveal the bit B to the receiver. Maybe they want to say, hey, I actually voted for candidate A, or something like that. And so they're going to engage in some interaction. And at the end, the receiver would have essentially have the envelope open, and they would see that, in fact, the committer did commit to the bit B. And in this phase, we require that the scheme satisfies what's called binding security. So what that means is, suppose that in the first phase, the committer committed to bit 0, then there should be no way for the committer to change their mind. So that at the end, the committer convinces the receiver that it actually committed to the bit 1, for example. Right? So basically, you just don't want the committer to be able to change their mind after the fact. Right? So that's what a commitment scheme is abstractly. You can imagine that this sort of thing is very natural in the context of cryptography. And indeed they are. They're used in all sorts of things like multi-party computation, zero-knowledge protocols. From the complexity point of view, they're quite interesting because in order for a commitment scheme to be secure, you are inherently or intrinsically assuming some computational assumptions. At the very least, you have to assume that, say, P is not equal to NP. So already what that tells you is that today, no one has a proof of a commitment scheme that's absolutely secure. Because if they did, they must have proven P is not equal to NP. But we're willing to make this assumption. And the reason for this assumption is that suppose both parties can solve NP-complete problems efficiently, then no matter what commitment scheme you come up with, either the hiding security or the binding security or both can be broken. So really in order to have this cryptographic security, you need to make some computational assumptions that both the committer and receiver are limited in their computational power. Okay. But this implication has some hidden assumption, which is that the scheme that I've described is a classical scheme. This is assuming that all the parties involved are classical computers. They can only perform classical computations. What happens in the quantum setting? So now let's talk about quantum bit commitments. And this is a question that came up in the early 90s when people were starting to think about, what is the power of quantum information? How can we use it for cryptography? So what if the committer and receiver can't take advantage of quantum physics? And so here things are a little more general. The committer and the receiver both have quantum computers. Maybe they can transmit qubits back and forth to each other. And in between the phases, they can be entangled. Right? So this is maybe the most general setting you can imagine. And what does hiding and binding security mean in this setting? So it's pretty natural. So after the commit phase, even though the committer and receiver have transmitted qubits, we still insist that the receiver cannot learn the bit B that the committer committed to by measuring her quantum state, right? So after the commit phase, the receiver has some quantum state on her side. By measuring it, there should be no way for the receiver to learn the bit B, at least assuming that they're limited in some way. Okay. And there's a reveal phase. They exchange more qubits, and the receiver will measure her state to verify the commitment to the original bit. Okay. And binding security, again, is the same thing. It just says that no matter what the committer does, there's no way for them to change their mind, right? Or fool the receiver into thinking they committed to the opposite bit. Hopefully the idea of a commitment scheme is clear in the quantum setting. So, in the 80s and 90s, there were cryptographers were fascinated. Oh, yeah.
Yeah, what line speed? Does 0 and 1 or it could be a
Oh, so here the bits B are still classical. So I'm still thinking of committing to a classical bit, but they can use quantum resources to do the commitment. Yeah, good question. I mean, these days people have extended to committing to quantum states and so forth, but let's just think about bits for now. Okay, so earlier I had told you this story of in order for a commitment scheme to be secure, you have to be making some computational assumption, at least in the classical world. In the 80s, people were excited by the prospect of getting an unconditionally secure commitment scheme if you're allowed to use quantum resources. And this was motivated by quantum key distribution, which is a cryptographic scheme for two parties to securely exchange keys. you can provably show that QKD is possible only based on the laws of physics without requiring unproven complexity conjectures. And this makes QKD obviously very attractive from a cryptography and a scientific point of view. And you might hope that, well, maybe we can extend this, this to quantum commitments. Well, wouldn't that be great? Sorry. So in 1993, some researchers, claimed success. They came up with a quantum commitment scheme that was, as they claimed, provably secure, just based on the laws of physics. And then a few years went by, and then Low, Chow, and Myers in 1996 said, actually, no, you didn't. There's a flaw in your proof. And what they said is that the security of quantum commitment schemes, even quantum ones, must rely on some computational assumptions, right? In order for these to be secure, you have to assume that at least one of the parties, or both, are limited in their computational capabilities. And there are two papers that came out at the same time. The first one is, they're a little more tentative in their title. They said, is quantum bit commitment really possible? I guess also it was written at IAS, which is interesting. And then simultaneously, there was Dominic Myers, who essentially proved the same result, and he was a little more firm in his title. He said, unconditionally secure quantum bit commitment is impossible. But they were really proving the same result. So how did their argument go? So let's imagine that someone came up with a quantum bit commitment scheme. Okay, maybe it's maybe quite involved, but we can always abstractly model it as the following. So after the commit phase, right, we can describe the joint state of both the committer and receiver as some, without loss of generality, a pure state. So let's call that state psi sub b. It depends on the bit that the committer committed to. Okay, so there are going to be different states possibly. And let's think about the marginal state of the receiver in this case. So if it was bit b, then the marginal state we'll call rho sub b. All right. Okay, so let's suppose, for contradiction, that both hiding and binding security do not require computational assumptions. Right? It means that no matter how computationally powerful the committer and receiver are, they cannot break this commitment scheme. So, what does that mean? So the hiding security says that rho 0 and rho 1 cannot be distinguished by any measurement. So rho 0 is the density matrix that the receiver has if the committer committed to bit 0. Rho 1 is if the density matrix if the committer committed to bit 1. And the fact that they both hide the bit b means that these two density matrices cannot, they have to be identical, or essentially identical, right? Okay. But then there's this something known as Ullmann's theorem. This is a very basic but very important result in quantum information, which says that if you have two pure states, psi 0 and psi 1, and they're quantum states they're bipartite quantum states, and I'll call the two registers of the states A and B, and they have indistinguishable marginals on the second system, on system B. Okay, so that means rho 0 is close or exactly equal to rho 1. Then, at least mathematically, there must exist a unitary, U, acting only on system A that transforms the first pure state to the second pure state. This is Ullmann's theorem. Such a unitary always exists. And I'm going to call this U an Ullmann transformation. Okay, so it's not too hard to prove this theorem, but it's super important in quantum information. And it quantifies how well one can locally transform one entangled state into another. Okay. All right, so this is Ullmann's theorem. How do we use it in this context? You can probably already see, well, the receiver's density matrix rho 0 and rho 1 are the same no matter which bit the committer committed to. So this gives a way for the committer to cheat, to change his mind in the reveal phase. So let's imagine that the committer first committed to bit 0, but after committing, he says, I'm going to change my mind. I want to convince the receiver that I committed to bit 1. So he can apply an Ullmann transformation on his side only. to map the global state psi0 to psi1, and then just continue with the reveal phase. Okay, so the committer will do some, apply some unitary to his side, and the global state will have changed, even though the committer only acted on this part. Okay, and then afterwards, the receiver will be convinced that the bit was 1, which is a contradiction of the binding security. So what this shows is that if the committer is allowed unlimited resources, the committer can change his mind, right? So if you assume that the scheme is secure, then you are implicitly assuming that the committer is limited in his computational abilities. All right, so that's quite interesting. So the security of any quantum bit commitment scheme, I mean, whether it's quantum or classical, is predicated on the hardness of performing Ullmann transformations. So as a complexity theorist, it's a natural question. How hard is it to perform Ullmann transformations? And this is an example of one of these fully quantum tasks, right? You're given a quantum system as input, and this is going to be the A system, and you just want to apply some unitary transformation so that the global system becomes some other pure state. What are the computational resources needed to do this? Can we relate the complexity of this Ullmann transformation to the complexity of other tasks? And thinking about this a little more, you come up to some very interesting realizations. So first, based on classical cryptography, we expect Ullmann transformations to be difficult, right? So here's a task, implementing Ullmann transformations. One thing that, essentially what this Low-Chow-Myers result says is that if you can implement arbitrary Ullmann transformations efficiently, you can break commitment schemes. So this less than sign means, this is easier than this, right? Like if you can do this, then you can do this. On the other hand, we know of classical commitment schemes that we believe to be difficult to break under the assumptions that one-way functions exist, right? Which again are, it's this bedrock of classical cryptography. So, assuming classical cryptography is, there are some difficult one-way functions to invert, even with a quantum computer, that should imply that Ullmann transformations are in general difficult to implement. Okay. All right, so that's a very simple implication. But what about upper bounds? Okay, so this tells us we expect Ullmann transformations to be hard, but just how hard is it? And can we put something on the other side, right? Can we say if something is easy, then we can easily implement Ullmann transformations? So, well, you say, can we reduce it to NP, right? Can we say that if you can magically solve NP-complete problems instantly, can you then efficiently implement Ullmann transformation? And you sort of scratch your head and you say, well, this is kind of an odd question. Like, how do I reduce this quantum transformation task to some NP problem, right? NP is the class of problems that you can efficiently verify solutions to. So you say, well, it's kind of hard to think about. Maybe let's relax my goal a little bit. Okay, maybe I'm not going to worry about NP problems. Let's say, can I even implement Ullmann transformations in exponential time? And something funny is going on here because EXP could mean multiple things. So one way that I can mean exponential time is, as in actually having exponential time available at your disposal. Okay? And the answer is yes. If you're given exponential time, you can certainly implement Ullmann transformations, right? And this takes some argument. You have to come up with an exponential time quantum algorithm, but you can do this. But what about the other notion of X, which in complexity world refers to, there's a precise definition of this, it refers to the class of decision problems solvable by exponential time Turing machines. And what this question is asking is, can this Ullmann transformation be efficiently implemented with oracle access to an X-complete decision problem? So the distinction here is I'm saying that you don't actually have exponential time at your disposal. I'm just giving you the ability to query an oracle who does. But this oracle will only solve classical input, classical output problems for you. Can you utilize this oracle to implement this Ullman transformation? And it's not clear, right? We don't know. Like, how do you convert this task of globally transforming this one pure state to another, and break it down into a small number of questions you can ask this oracle? We don't know. So let's relax our goal even further. Let's say we can query the oracle not for exponential time decision problems, but we can ask it to solve even uncomputable problems, like the halting problem, right? No one can solve the halting problem, but let's say I gave you an oracle who could. Can you then efficiently implement Ullman transformations? And we still don't know the answer. Okay. This brings us to something that is called the unitary synthesis question that really kind of encapsulates this mystery. So I'll first formally state what the question is, and then I'll explain how it's related to this previous thing. So this is a question raised by Aronson and Kuperberg in 2007. And they ask, can every n-qubit unitary U be implemented by some polynomial time quantum algorithm that gets to query some Boolean function that depends on the unitary? Okay, so here this Boolean function gets to depend arbitrarily on the unitary U. The only thing is that the number of input bits to this unitary has to be limited to some polynomial. Okay. And yeah. Does there exist an encoding? Right. Exactly. So, given this unitary U, you get to design your favorite Boolean function that tells you some useful information about the unitary U to implement it efficiently. Yeah. Okay. And the only constraint that I'm putting is that this quantum algorithm has to run in polynomial time, but this Boolean function can be arbitrarily complex, right? It doesn't even have to be computable. In other words, what this question is asking is, can the complexity of this unitary be pushed off into the complexity of some decision problem? And the conjecture is no. There exist unitaries that are just so fundamentally quantum that there's no way of reducing it to just a small number of questions to a classical oracle. And this question has stood open since 2007. It's still open. There was some non-trivial progress, actually some amazing work by Lombardi, Ma, and Wright last year that showed that if your quantum algorithm gets to ask one query to the Boolean function, then it cannot implement every unitary. Okay. But of course, there's a big gap between one query and polynomially many queries. But this is the frontier of what's known. Okay, so if we really believe that the answer to this question is no, then it tells us that somehow this task of implementing unitary really is somehow, at least complexity-wise, kind of independent of the complexity of Boolean functions, right? I mean, this is something that we know some things about, but what this question is really asking is, can we port any of this understanding to the the unitary world, and at least in general, maybe not. And why is there some disconnect between these two worlds of classical input, classical output versus these fully quantum problems? And it's the usual suspects, right? Their quantum information is different. There's things like the no cloning theorem. There's the fragility of quantum information that makes these fully quantum problems somehow, they seem fundamentally different. I mean, for one thing, when you get a quantum state as input, you can't make a copy of it. So in some sense, you just have one shot at implementing the transformation that you wanted to, right? Whereas with, you can imagine with classical algorithms, you get a classical input, there's often, if you fail to solve the problem once, you can try again, right? And so you make a new copy of the input. With quantum input problems, this seems, you can't do this in general. And there's some sense in which oracle access to classical functions, even fantastically complicated ones, don't help to shortcut a difficult quantum transformation. Okay. I mean, there's some other evidence that's also emerged that's really kind of, shed some insight on how different these two worlds are. Maybe I'll mention this one, which is something that was realized recently, which is even if P is equal to NP, okay, we don't think this is true, but even if it were true, this would be bad news for essentially all of classical cryptography. You can break any classical crypto scheme for the most part, but we can still have cryptography. And that's by using computationally secure quantum crypto, like a quantum bit commitment scheme. Okay. So that's quite interesting. Okay, so this is sort of motivation. This first part of the talk is motivation for why I think we need, there really needs to be a sort of a separate theory to explain the complexity of these tasks. So if we do need this theory, what do we want to do in it? So here are the goals. I mean, these are the goals of any complexity theory, but the first important thing is we want to identify natural tasks from the sciences, right? What are interesting computational tasks that people, for their own reasons and own motivations, are thinking about? And once you collect all these different computational tasks, you want to show how they're related. How do they reduce to one another? If you can solve one, can you solve another? Can you classify them by their complexity? Can you identify complete problems? Can you prove separations, right? Can you show unconditionally that one problem is strictly harder than another? And can you use the hardness of some problems as a basis for cryptography, right? These are all goals of what you want from some complexity theory. Okay, so in the sort of the second part of this talk, I'm going to give an illustration of some of these goals. So first, let's go on Safari. Okay, we're going to go on Safari on the computational landscape. We're going to look around and see what problems people are thinking about naturally. So you look over to where the quantum Shannon theorists, and they really like studying this workhorse of information theory, which is state compression. Right? This is a task of you're given a quantum state, can you compress it to its entropy? Very fundamental task in information theory. You look over to the people who are thinking about quantum error correction, and they're really interested in the task of decoding noisy quantum channels, right? This is some task you like to do. You get noisy quantum information out, you want to clean it up, output clean quantum information. The quantum cryptographers are trying to think, well, how can I break quantum cryptography, right? What are the tasks needed to do so, right? How can I do it efficiently on a quantum computer or not? Over in the swamp, there's some complexity theorists who are thinking about things like optimal prover strategies and a quantum interactive proof. And, or we come over to a place like here, and people like to think about this task of unscrambling the Hawking radiation of a black hole. So, all of these are fully quantum tasks, quantum input, quantum output, and they all seem quite different. And you ask yourself, if you're sort of going on safari, like what relates all of these animals to each other, right? Are they related in some way? And what turns out, sort of the connecting thing is the Ullmann transformation. Okay, somehow what we'll find is that the complexity of all these tasks can be explained by this abstract task of performing an Ullmann transformation, which may or may not have been obvious a priori. So to really kind of make these lines and these connectives more precise, we first have to have sort of a language to even say what it means for these tasks to be equivalent to one another. And so let's do a little bit of formalism, but not too much. So I'm going to define what I mean by a unitary transformation problem. Okay? Or sorry, unitary synthesis problem. So this is going to be a family of unitary transformations, right? So each of these u sub x's is some unitary acting on some Hilbert space. And all of these x's, they're bit strings, okay? So all of these unitaries are indexed by a bit string. So, what this means is, the string x is going to tell us what unitary we want to implement. Okay, that's going to specify the unitary, and it's going to specify it to our quantum model of computation. Like maybe this is a quantum computer, maybe this is some protocol, or something else. And then the input to this model of computation will be some quantum state. And we want the outcome of this computation to be the unitary indexed by this specification applied to the input state. So that's the task, right? When I come up to you with this unitary synthesis problem, I'm really asking, can you perform this task with your model of computation? Okay. And we say that a model of computation implements it if you actually perform this successfully, or at least perform it approximately, right? Like maybe you don't have to produce this output state exactly, but up to some approximation, you have to do it. That's a good question. So I think of x and theta as conceptually different things. So x it's sort of written down on a piece of paper, like it's giving you a handle on what unitary you want to implement. Okay. I mean, the simplest case of this is like x is literally the description of a quantum circuit. But there are more interesting cases that I'll describe in a second. So yeah, you can think of it as you can think of it both of them as inputs, but they're serving different roles. So in some sense, this x is kind of the input that you can copy, whereas this theta is sort of the quantum input that you have just one shot of applying the unitary to. Yeah, I mean, of course, a classical input is also quantum input, but I think conceptually, I think it's useful to separate them. Yeah. Okay, so that's what it means to implement this task, and you have to have some way of measuring complexity, and that's up to you. Do you want to measure time, space, non-determinism, whatever it is, but complexity should be measured as a function of the length of the string x and the number of qubits of your quantum state theta. Right? It's just like in classical complexity theory, we always measure complexity as a function of the input length. Okay, so same thing here. Okay, so we have our notion of of a unitary synthesis problem. There could be many different types of unitary synthesis problems you're interested in, and we want to organize them into complexity classes. We want to sort them by how hard is it to implement them. So we can already, just by analogy to the traditional complexity world, define some complexity classes. So first, let's define the notion of unitary BQP. This is the class of all unitary synthesis problems that can be implementable by polynomial time algorithms. Okay? So if you had polynomial time on a quantum computer, you can implement these unitaries. Very natural. Here's another class, unitary p-space. These are sets of problems that are implementable by quantum algorithms that don't necessarily take a small amount of time, but you limit the amount of memory they have. They're restricted to using a polynomial number of qubits to solve the problem. It's, in traditional complexity theory, p-space contains BQP, and we believe that it's vastly bigger than BQP, right? So having, small space, but unlimited time seems to be a very powerful resource. So similarly, you can define the unitary complexity analogs of this. And finally, sort of for the last bit of formalism, we have classes, and now we want to say, what does it mean for one problem to reduce to another? Okay, so you have to introduce a notion of reduction. Okay, so let's say you have two unitary synthesis problems. You have two sequences of unitary. So you have u sub x. You have v sub y. And you say that u, polynomial time reduces to v if there's some polynomial time algorithm that gets to query v and then, by querying v, efficiently implement the first problem. And essentially what that means is if this unitary synthesis problem v turns out to be easy, then u also turns out to be easy. Okay? So this is sort of a diagram of what a reduction looks like. You want to implement u sub x, and in order to do so, you say, well, I'm going to call as a subroutine v sub y. Sort of a very natural notion of reduction. The way we define it, just to keep things simple, we say no, but of course you can define like superposition, query access, and ask, what does that buy you? And I don't know. But at least I'm just thinking about,
Yeah, so you don't take that. Yeah, for now, I'm just
thinking of the specification Y is just a classical, it's like hard-coded into the algorithm, to this query algorithm. Yeah. Okay, so that's the formalism, but essentially that's all we need to really get going with this theory. Let me introduce the.
So what does it mean? So yeah, Y depends on X, but not on theta.
Depends on X in a way which is classically computable or quantumly or.
Let's say
Classically. Of course, you can add more bells and whistles, but let's take the simplest setting for now. This notion of reduction is enough to capture what I want to say.
okay. So here's the start of our show. This is a unitary synthesis problem that
Really is, in this talk, the most important one. This is the Ullmann transformation problem. So what are the unitaries and what are these subscripts X? So X here, it's going to be some classical string that specifies circuits for two bipartite pure states, so psi 0 and psi 1. Okay, so you can think of X as writing down on a piece of paper these two circuits. Okay, and these two circuits will each have two registers, A and B. And whenever you write down two pure states in this fashion, Ullmann's theorem will tell us that there's going to be some unitary that depends on these two states that will locally map psi 0 to approximately psi 1. Of course, this will depend on how close are the marginal states of psi 0 and psi 1, but let's assume for now that they're the same. Okay. So for every pair, every time you write down a pair of circuits, this is implicitly describing some Ullmann transformation, right? Some unitary. Make sense? And so whenever I give you this X, that's really instructions for saying, I want you to implement this use of X. Okay, so let's do some complexity theory. And first I will say that what I'll talk about, all of this is really based on work with a bunch of people. So John Bostanci, Yuval Efron, Tony Metker, Alex Paremba, Lowen Chen, and Greg Rosenthal. And also there's a disclaimer, I'm going to be stating some theorems, but these are going to be approximate theorems. There's technical details and so on that for simplicity I'll just omit, but hopefully I'll convey the essence of what I want to talk about. Okay, how am I doing on time? Good. Okay, so let's go back to our landscape. And we have all these different problems. And how can we relate them to each other? So here's the first theorem. This Ullmann transformation problem is in unitary BQP, meaning that there exists a polynomial time algorithm to implement arbitrary Ullmann transformations, if and only if this Harlow-Hayden task is also in unitary BQP. So the Harlow-Hayden task is some formalization of the task of unscrambling the Hawking radiation of a black hole. Okay? They define it a certain way, so we're going to call that computational task the Harlow-Hayden task. And it's maybe not surprising that one direction holds, right? Like the way I set it up, it's clear that the Harlow-Hayden task is reducible to Ullmann transformations, right? If you can solve any Ullmann transformation, you can certainly decode any black hole radiation state. But it turns out that the converse is true, okay? And that comes from the way they defined it. This task is expressive enough to embed any other Ullmann transformation task. All right, so that's one thing we can say. Here's another task. This comes from quantum cryptography, for breaking quantum commitments, which I just talked about. It turns out that the task of implementing arbitrary Ullmann transformations and breaking any quantum commitments, these are also equivalent, right? If one is easy, then the other is easy, and vice versa. Okay. Right. Again, commitment scheme, quantum commitments might seem like a thing that's specific to cryptography, but it turns out that it's expressive enough to encode any other Ullmann transformation task. Okay. Here's another one that they turn out to be equivalent. So, this Ullmann transformation problem is also equivalent to this task of decoding noisy quantum channels. Okay. Or, what I mean here, there's some way of formalizing it, but under this formalization, you can show that these two problems are equivalent. Okay, so an easy corollary is that all of these problems, decoding noisy channels, breaking quantum commitments, unscrambling radiation, these are all computationally equivalent. Okay. Which again, this is something that you might have not realized a priori, but it's one of these things that you realize when thinking about this, these problems in this way. And this is maybe not the first time that this has been observed. There was a paper a couple years ago by Zvika Brzezinski titled "Black Hole Radiation Decoding is Quantum Cryptography." And what he really meant by that is, he's showing that these two problems are equivalent. But in fact, more can be said. All three of these things are equivalent. Okay, so now we have the language. We can actually somehow characterize, say all of these things really are one and the same computationally. Here's an example of a problem that the story's not quite fully fleshed out yet, but that's one of quantum state compression. Again, this is a task of, I give you a description of a quantum state. Does that allow you to efficiently compress that quantum state to its minimum entropy, or the size dictated by its entropy? Information theoretically, this is always possible, but can you do it efficiently for all states? One thing we can say is that if Ullmann transformations are easy, then you can compress any quantum state to their entropy. That's quite nice. But the converse is not, we don't know what the true converse is. So we can prove an almost converse. If quantum states can be efficiently compressed, then pseudo-random states and pseudo-entangled states do not exist. Right? Essentially, this comes from the fact that if you had such a universal efficient compression scheme, you can use that to distinguish between whether a state was truly entangled or pseudo-entangled, okay? Or pseudo-random versus truly random. And we don't quite know yet that this implies that the Ullmann, that you can use such a universal compression scheme to implement any Ullmann transformation. And so one question that I particularly like is to really understand this, like, is this quantum state compression actually easier than Ullmann transformations, or are they equivalent? So this is an open question. Okay. All right, so there are some examples of some computational tasks. We've related them to each other. But can we really come up with some abstract characterization of just how difficult the Ullmann transformation problem is? I said before that if you assume quantum secure one-way functions exist, the Ullmann transformation problem is going to be difficult. In terms of upper bounds, we know that we can solve it in polynomial space. I mean, you require exponential time, but you don't need exponential amounts of memory. Okay? And the techniques for doing this, we'll use something called the quantum singular value transform, which hopefully I think you'll hear from Yuen Tang's talk tomorrow. So there's some lower bounds, meaning that we don't believe it's in unitary BQP. There's some upper bounds. We think that it's contained in polynomial space. But can we pin it down, the complexity of this problem, more precisely? And the way to do that is to say that it's a complete problem for some natural complexity class. If you've done that, then in some sense, you've really kind of identified like the essential character of this problem. And it turns out that you can, and it's quite interesting. And we didn't expect this when thinking about it, but it turns out that there is an interactive proof characterization of the complexity of Ullmann transformations. So what's an interactive proof? So let's imagine that we have a polynomial time verifier, represented by Mickey Mouse here. Okay, so Mickey Mouse can only perform polynomial time quantum computations. And its goal is to transform psi 0 to psi 1 via some local transformation. Right? You can imagine that the verifier here is like trying to break a commitment scheme or something. Right? It has to perform some Ullmann transformation. But as just argued, it's unlikely that Mickey Mouse here can efficiently do it. So let's give Mickey Mouse a little more help. Let's have the verifier talk to an all-powerful but untrusted prover. So here Merlin is quite computationally powerful, can do anything you ask it to. The only issue is you don't quite trust Merlin. So is there a way for the verifier to interact with this prover in such a way that the verifier can implement this difficult unitary transformation, but in a way that the verifier actually has confidence that the prover helps it do the correct transformation and not something else? And at the end of the interaction, the verifier will say either accept or reject. If it accepts, then it should have high confidence that the final pure state should be psi1. And it turns out that there is an efficient interactive proof for the Ullmann transformation problem. Okay? And I'll explain how it works. So here's step one. The polynomial time verifier is going to receive register A of this entangled state. So this global state is called psi0. Okay. Step two, this polynomial time verifier is going to synthesize its own copy of psi0. And it can do this because we're assuming that psi0 and psi1 are efficiently synthesizable, right? Like these are prepared by polynomial size circuits. Okay? So in its internal memory, it's going to have register A of the true copy. And it's also going to have this other copy of psi0. So we're going to call this the decoy copy. The verifier is going to randomly permute the A systems of the true copy and the decoy copy. I mean, maybe it switches them or maybe it keeps them the same. Let's say for now that it switches the decoy and true copy. So now this system is entangled to this, and this one is entangled to this. Okay. What's important is that this prover has no idea whether it was permuted one way or the other. The verifier is going to send the A registers of both systems to the prover, and it's going to ask the prover, can you please apply the correct Ullmann transformation to both systems? And of course, the prover can do anything at once, but the idea is hopefully it applies the correct transformation. So the prover is going to do something. It could entangle the systems, who knows what, right? This can be some complicated entangled mess, but it's going to send both systems back to the verifier. And the verifier will unpermute the systems, okay, right? And then the verifier is going to test whether the decoy copy is now in the state psi1. And again, it can do this because psi1 is something that's prepared by a polynomial size circuit. So the verifier can simply apply the inverse circuit to this state and check whether it started in, say, the all zero state. If so, then it's going to accept. And then it's going to output this A register. So let's say it does. And the point is that suppose this decoy copy really ended up in the state psi1. Since the prover didn't know which was the decoy copy and which was the true copy, the verifier is going to have high confidence that the true copy really had the Ullmann transformation applied to it.
Why couldn't the untrusted prover do it correctly one for one?
Because it doesn't know ahead of time which one is the true copy. So let's say it decided to do the correct one here, but the incorrect one here.
It doesn't know, but maybe by chance 50% of the time you might think.
Good. So here the confidence is not so great, but you can imagine doing this many times. So you have, instead of one decoy copy, you have many. And the more decoy copies you have, you can sort of hide your true copy in one of them, and the prover doesn't know which one.
Is the prover allowed to entangle the two qubits you gave it with each other?
It can do anything, yeah. So it can entangle the two.
And put some other qubits in. There's nothing except the only way to check is you do this test at the end where you check whether the decoy copy ended up in psi1.
You check the decoy copy without effects on the copy?
It could have an effect, like it could collapse the state, but if the decoy copy ended up in psi1 and then this collapses somewhere else, then where it collapses to will end up being close to psi1. I mean, provided you have let's say 100 decoy copies. So hopefully you get a sense of how this interactive protocol works. And the point is here that, again, Ullmann transformations are difficult, but here's a way of verifying that someone has helped you implement this difficult transformation on some states. What does this tell you? So this tells you that the Ullmann transformation problem is contained in another complexity class that I'll call Unitary QIP, which stands for Quantum Interactive Proof. And this is a class of unitaries that you can implement in this manner, right? You interact with an all-powerful prover, and you can verify that at the end of the day, the unitary has been implemented. There's something more you can say. So in fact, this interactive proof that I just described to you is something called zero knowledge, which is a concept from, again, from cryptography. And it means that the verifier can efficiently simulate each step of the protocol without needing the prover. And if you haven't heard of this before, that sounds absolutely crazy, right? Because it seemed like you really needed the help of the prover. But it's just saying that at least from the point of view of the verifier, like nothing that it sees is surprising. Okay, like you didn't learn anything about how this unitary transformation was implemented in some sense. And zero knowledge interactive proofs gives rise to some class called Unitary SEK. So ZK stands for zero knowledge. And it turns out that this Ullmann transformation problem is a complete problem. What that means is there exists a zero knowledge protocol for Ullmann, but in fact, every zero knowledge, any unitary that can be implemented in this zero knowledge fashion can be solved by Ullmann transformations. Okay? Right? It's just like, in the sense that saying 3-sat is an NP-complete problem, right? So 3-sat captures NP completeness. The Ullmann transformation problem captures completeness for zero knowledge, which is rather interesting. Okay, so somehow we've really put a home, given this Ullmann transformation problem in the home. And let me say one more thing. So you can define a variant of the Ullmann transformation problem called succinct Ullmann. So here states psi 0 and psi 1. Now I'm going to say they're no longer efficiently preparable, but they have some succinct description. So here's an example. Maybe psi 0, you say, is the result of time evolving a simple state by a Hamiltonian for exponentially large times. Okay? I mean, this is a succinct description, but of course, actually preparing this seems very difficult. It takes exponential time. So succinct Ullmann is implementing the Ullmann transformations for these types of states. And this problem, it turns out to be complete for unitary QIP. It's also complete for unitary p-space, right? What this tells you, it's the hardest problem in this class, unitary p-space. And as a corollary, this implies that these two complexity classes are one and the same, right? And this mirrors something that was known in traditional complexity theory, that the types of problems you can solve in an interactive proof are incredibly powerful. So in fact, they're one and the same. Okay, so we have some results here, and we can start drawing out what this unitary complexity landscape looks like. So down here we have unitary BQP, problems you can solve a polynomial time. So example is Hamiltonian evolution, right? There are efficient quantum algorithms for time-evolving Hamiltonians. There's this unitary SEK, which I just said the Ullmann transformation problem is a complete problem for. And as we've seen, it's equivalent to these other problems: decodable channels, breaking commitments, unscrambling radiation. This compression problem is reducible to Ullmann, but we don't quite know the full story here. And way up here, we have p-space and unitary p-space and unitary QIP, right? The succinct Ullmann problem is complete for unitary p-space and QIP. The task of fast-forwarding the time evolution of a Hamiltonian is reducible to this, because but they could be equivalent. We don't yet know. So yeah, so we're starting to see that there's some structure in these problems. And what these, we don't know that any of these containments are strict, right? Like it could be that all of these classes are equal, but it's reasonable to suspect that, unitary BQP is a smaller class than unitary SEK, which in turn is a smaller class than than unitary p-space. Okay, so the last part of the talk, I'll sort of say, try to give a little more motivation for this. So, it seems like so far I've just introduced some alphabet soup of complexity classes. I've done some taxonomy of sort of classified and identified which problems belong in what classes. But why are we doing this? And here's an attempt at some answers. So I think a great lesson from complexity theory is that the computational universe is much richer than just the distinction between polynomial time and non-polynomial time. Right? I mean, it's sort of an initial reaction one might have is to think, polynomial time are the ones that are efficiently solvable, fine. And if it's not efficiently solvable, we don't care about it, right? It's just hard. But complexity theory tells us that not all hard problems are created equal. There's actually structure. There's different types of hard problems. And understanding the structure and relationship between these hard problems gives a lot of insight back into what's solvable in polynomial time. So that's one lesson. Showing that a computational problem is complete for some natural complexity class, which you might define by thinking about different computational resources like space or time or interactivity or post-selection or something. If you can show that a problem is complete for such a complexity class, this illuminates something essential about the problem. Okay. And developing this theory, I think, gives us, the hope is that it can give us a useful and succinct language to ask interesting questions about the complexity of these fully quantum tasks. So, here are some examples. People study quantum Shannon theory for a very long time, several decades. Right? They come up with ingenious protocols for doing all sorts of things like quantum state compression, redistributing entanglement from here to there. But all of this has been considered without consideration of complexity. And some of these protocols appear quite difficult to implement. And you can ask, well, how hard are these protocols to implement? Can they all be polynomial time reduced to, say, the Ullmann transformation problem? Right? Now, this is a question you can ask, and we have a language to answer it. I mentioned this before, is the task of fast forwarding the time evolution of a Hamiltonian complete for unitary p-space? Right? Is it the hardest problem in this class of problems? Here's a quantitative version of the Aronson and Kuperberg unitary synthesis question that I asked. So let's take the class unitary BQP, right? So these are problems you can solve efficiently, unitaries you're going to implement efficiently in polynomial time. And let's say I augment it by giving it oracle access to a classical polynomial space oracle. Does this give me the set of unitaries that I can implement in polynomial space? Right? We don't know. This is sort of a fine-grained version of the unitary synthesis question. And again, we don't even know if this inclusion is, even if I give you access to the halting problem, can you implement polynomial space unitaries? We don't know. I think another useful thing that thinking about this brings up is it makes you think of new models. Okay, so I'm going to define another complexity class called unitary QMA. And this is an analogy to QMA from traditional complexity theory, which I said captures the complexity of estimating ground energies of local Hamiltonians. And I'm very interested in what's a complete problem for this class, or what's even contained in it. And the reason I think it's interesting is because it models the following scenario. The prover is going to send the verifier some polynomial size quantum state that helps the verifier implement a complicated unitary transformation. So it's only interactive in some one direction. So the prover will just hand the verifier some state and then says, you use that somehow. And it's kind of asking, when can a quantum state catalyze a difficult computation? And I think we don't really have a good sense of when this is possible. So I think this complexity class captures tasks of this form. Another complexity class you can think of is that of post-selected unitary operations. All right, you want to implement some unitary, but you allow yourself the ability to post-select. And again, what's in this class? How does it compare to other unitary complexity classes? And this is motivated by some recent works and stuff in quantum gravity, like I guess things like considerations of the Python's lunch or the unitarity of the black hole S matrix. Here, people you read these papers and they're talking about post-selected unitary computations. And hopefully thinking of these questions in this unitary complexity framework could help shed some light on the complexity of these operators. Okay, and let me end with some other future directions. I think probably the most important question in this area is to really hopefully settle this unitary synthesis question. If the answer really is no, as we conjecture, that really tells us that the worlds of traditional complexity theory and this unitary complexity theory are kind of independent, right? You can't understand traditional complexity theory to fully understand unitary complexity theory. Some goals would be to, maybe you can prove unitary complexity separations or inclusions that don't hold in decisional complexity theory. Yeah, maybe finally, can this unitary complexity theory sharpen the use of complexity in high energy physics, right? This is something that's, I guess, in vogue these days, and hopefully having a precise formal language to really ask these questions could, be of some help. So with that, I'll end here and take questions.
Yeah.
You had a comment on your slide with these different complexity classes that there's also average case, if I read it correctly.
Yeah, so that.
Yeah, so
this is part of the technical details that I was sort of. So, how exactly are these classes defined? I mean, I kind of gave you a high-level description, but by average case, I mean that really you only insist that the unitaries be implemented not for all possible input states, but let's say for most input states of some distribution of your choice. And the reason for this is sort of makes a lot of the problems like, it just makes sense for a lot of these problems where you only care about implementing the unitarian over some distribution of quantum states.
Question? If not, let's go to the tea break and then we'll go to the discussion groups.